let's get the show on the road. Hello, everyone. Hope you're well. Welcome to the last edition of Math 1206, Summer 2021. Let us jump into it. So let's, first things first, recap from yesterday, which includes talking about the final. Final is in 2 days, and it starts officially in 2 days, and I give you about a 2-day window to actually complete it. So I just wanted to remind you of that. So, and I mean, I'll probably bump this up to 3 hours just to prevent any technical difficulties. So yeah, file's going to be about 3 hours long. That includes time to upload all your work. It's going to be about twice the length of a regular test, just about. And it's going to include pretty much up to everything that we did yesterday, and everything that we talk about today would be bonus material. So yeah, it starts on July 2nd at 9 a.m. and it will be open until July 4th at 9 a.m. and just in time for you to wrap up and enjoy your 4th of July weekend. And that's all Eastern time, by the way. So maybe so let's actually talk about that a little bit. Announcements. Final. July 2nd at 9 a.m. to July 4th at 9 a.m. Eastern time. And a 3-hour window, including upload time. Topics. So covers everything from the beginning of class to the lecture on yesterday, 6/29/21. Material from 6/30/21 will be bonus material. Except I'll mention a little bit more about errors between curves, which we did yesterday, and I pretty much told you everything that you would, I think, need to know about that. But I'll talk a little bit more about it today. But it would be included on your regular test. But that's the gist of it, and I would say, including, but perhaps not limited to. So I'm just going to say some things off the top of my head that I think I included and I think are important. So one, computing limits, computing derivatives, including implicitly. computing integrals, including substitution. Using both parts of the fundamental theorem of calculus, approximating areas with finite Riemann sums. That's like the left-hand rule, right-hand rule, midpoint rule kind of thing. Finding areas with infinite Riemann sums. Conceptually, computing tangent lines. Finding f prime from definition. Verifying continuity. Including finding unknown values that make functions continuous. That's like when I gave you the function where there was like an a and a b in it, and I said, oh, find a and b that makes this function continuous. So problems like that. Related rates. So there'll be one related rates problem. There's going to be an optimization problem. There's going to be a curve sketching problem. Finding absolute max min problem. That's the closed interval method. Mean value theorem or Rolle's theorem. I probably won't ask you the intermediate value theorem. I don't want to ask about too many theorems. I guess if I'm going to ask about like verifying the parts of a theorem and using it to answer a question, I would probably go with like a mean value theorem, or a Rolle's theorem. It can be very, very similar. So, and again, when it comes to computing limits, derivatives, and integrals, of course, that's going to be like, several parts. Like A, B, C, D, maybe A, B, C, D, E, something like that. But technically, these are things that I'm hoping that you'll be able to do relatively quickly per problem. What else? Maybe some applications of integration. Did I already say that? Errors between curves. Physics of motion application. That's just like when, oh, here's the position function, find velocity and acceleration. Or something gets thrown off a cliff, all you know is the acceleration. Find the function that describes its current position, ignoring air resistance and all that. or find the time when the object will hit the ground or something like that. Approximating values with linear approximation. What else? Maybe throw in an average rate of change problem for easy points, which is a lot. That's so that will cover pretty much everything. So bonus would be, well, stuff we do today, stuff in today's class. So maybe I'm hoping I get to integration by parts. Things like average value of a function. What else do I want to talk about? Distance and displacement. Maybe mean value theorem for integrals. I don't know. Yeah. So something like that. So if as I was saying these topics, you have a fairly good idea of how to do them, that's great. But if you're going to review, of course, for a lot of these, you just need to know the basics about, just basic algebra skills, how to find derivatives and integrals, how to find limits, including using L'Hopital's rule, all the techniques that I gave you, when to use which technique. And yeah. So straightforward stuff, I think very standard as far as Calc 1 final exams go at university. So nothing out of the ordinary. But I just thought I'd mention some things. So I think that being said, I want to move on now, but if there are any questions on the final or any concerns about the final, like I'll take those if you have them. Okay. So let's pick up where we left off. So we will talk about today one applications of integrals. So I'll say some more on area between curves. I did mention that, right? Areas between curves, yeah. Like I said, distance displacement. Average value. Maybe, I don't know, depends on the mood. I don't know. And like how long it takes me to cover the previous three. Maybe mean value theorem for integrals. into new integration technique. It's going to be called integration by parts. So essentially, I taught you integration by substitution. We did that yesterday. And that is essentially the reverse of the chain rule. So of course, you have the chain rule, the product rule, the quotient rule. So you might wonder, how do we reverse all the others? Well, integration by parts is going to be the reverse of the product rule. So we're going to talk about that. There is no reverse of the chain rule. Technically, remember we use the product rule to derive the form for the quotient rule. So it turns out you actually don't. The quotient rule is just something that makes your life a little nicer, reduces the amount of simplification you have to do. But strictly speaking, you can only use the product rule and get away with everything. Because if you have f divided by g, you can just write it as f times g to the -1 and apply the product rule. And that's how we actually did it to find the derive the formula for the quotient rule. So once we have an integral rule that covers the product rule, we don't really need one that covers the quotient rule. We could derive one, but it would actually be too complicated. It's not worth it. You just want to bring it up and treat it like a product rule kind of thing. It's helpful in the derivative case, but not that useful in the integral case. All right, so let's get into it. So we're just essentially having fun today. All right, cool. Let's move on. More on areas. We saw yesterday that if we have f of x greater than or equal to g of x on AB, then if A is the area between f of x and g on AB, we have that our A would be just the integral from A to B of f of x minus g of x dx. Or in other words, generally what you want to do is that it's going to be top function minus bottom function. Which I'd probably actually prefer you think of it that way, believe it or not. Especially when eventually you're going to realize that there are a lot of things coming up, especially like in Calc 3, for example, where just positional awareness is going to mean a lot. So top versus bottom, right versus left, up versus down, that sort of thing. Just being able to think in terms of what position something is in relation to something else, that's going to be very, very important conceptually moving forward. And not just in Calc 3, even as early as Calc 2, that kind of knowledge is going to come in handy when you're setting up certain problems. So I just want you to think in terms of top versus bottom, not necessarily, oh, this function is called f and that one's called g. That's not the point. You want to take the higher one and subtract the lower one at all times. So that was the idea. And sometimes A and B are found via intersection points. As they were yesterday. And sometimes AB is given. So I can just tell you flat out, I want the area between these curves on this interval, or I can say, oh, just find the area between the curves, and then you just want to find the natural place where you have an area stuck between both of them. And you can find that by using like intersections. So what else do I want to do? Also, we will want to free ourselves from thinking of X as the only possible independent variable versus Y. So this will start a little bit in Calc 2, I think, especially if you do a topic like volumes of revolution, you'll see it come up. It'll actually also be very, very important in terms of finding integrals and describing spaces in 3 dimensions in Calc 3. But the idea is you don't just want to think in one direction like, oh, X is always my input. I always erect rectangles vertically, because you can actually think of Y as an input variable and think of everything horizontally, like do horizontal rectangles. So it is possible to do an integral with respect to Y, for example, with a dy. So I just want you to be aware of that. Consider finding the area between something like this. So I'm just going to describe a picture to you. I'm not going to really give you a function. So it's like a parabola, but a sideways parabola. And this part right here. So we can call this f of x. Well, it won't be called f of x technically. So we can call this, say y equals g of x. And here, something like y equals the positive radical of f of x versus here y equals the negative radical of f of x, or something similar, right? So this is describing the part above x-axis, and this is describing the part below x-axis. Okay. So you can think of this even as like x equals y squared. So the top would be y equals the positive radical x. The denominator would be y equals the negative radical x, right? So you could have a function described like that. Of course, it's not a function with respect to x, but it is a function with respect to y. And yeah, so you could have something like that. And let's say we have intersection here, and this is at A. We have an intersection here, and this is at B. And let's say we know the y intersections as well. Let's say this is C and this is D. And suppose we care about this area in here. We want to find the area. Now, what I want you to realize is that if we were to use, if we used area is the integral of top minus bottom dx, notice what would happen. there's going to come a point where at point A and B, your top changes, right? You'll notice that if I looked, say, here, notice that on 0 to A, y equals the positive radical of f of x is on top, and y equals the negative radical of f of x is the bottom. But on, say, A to B, this actually changes. Notice that once you cross this vertical line right here, the situation actually changes. Between A and B, the red curve is on top and the blue curve is on the bottom. So here, this guy's still on top. But now y equals g of x is bottom. So notice that the bottom part changes. Different lower functions. So we would need DOS integrals, right? Which can be annoying. So you would have to say, in this case, the area, if it's the integral of top minus bottom, then there's going to be a different top and bottom from 0 to A as there is from A to B. So from 0 to A, you would have the radical of f of x minus the negative radical of f of x. And here you would have radical of f of x minus g of x. Because you would need two separate integrals to account for the two separate pairs of the top functions and the bottom function. Okay. Now, versus, we tilt our head to the side. And imagine the y-axis as that of the independent variable. Okay. So let's say we look at this exactly the same picture, right? So nothing has changed, but now instead, what I'm going to do is I'm going to think of this as, say, x equals some h of y function, right? So it's like I'm turning my, tilting my head to the side, and now I'm just looking at this as it were a parabola. And I'm imagining that the y-axis is kind of just like the x-axis. And this guy here also, now I think of it not in terms of x, but in terms of y. So like x equals p of y. Right? Now, it's the same area. It's just that, and the same curves, it's just that instead of saying y equals some function of x, I describe them as x equals some function of y. And I tilt my head to the right. And you would create intersections here and here. So now the y-axis is what I'm looking at. And now what you'll notice is that this guy is the right function, or it's the guy with the larger x values. And this guy here is the left function. And he has smaller x values. Now notice on the entire interval C to D, there's only one right and only one left, right? It never actually changes. It's not like up here where on 0 to A, I have a different top and bottom versus from A to B, I have a different top and bottom. If I tilted my head to the side, there's only one guy that's always on the right. The blue is always on the right. On the y-axis interval CD, and the left function is it's always on the left. On CD. So it turns out I can think of the area as the integral from C to D of instead of top and bottom, as right and left. And you do right function minus the left function. And this time you do it dy. So you'd solve for all curves in terms of y, and you would do it that way. So I don't know if I can give you an example off the top of my head. Find the area between the curves, say x equals y squared and y equals x minus 2. Yeah, that should work, something like that. So you would get a picture similar to what I had here. X equals y squared is going to be this graph right here. And y equals x minus 2 is going to be this guy right here. This is going to be at 2. And I want to find this area. So just as before, I can find the intersection. So I know that I have x equals y squared, and I have x equals y plus 2. This means I want y squared equals y plus 2. This means I want y squared minus y minus 2 equals 0. This means I want y minus 2 times y plus 1 equals 0. This means I want y equals 2 or y equals minus 1. So this here would be minus 1. This here on the y-axis would be 2. And so now I can say the area is going to be the integral from minus 1 to 2 of the right minus left dy. And this is going to be equal to the integral from minus 1 to 2 of the right function is going to be y plus 2. And the left function is just going to be y squared. And you can actually continue. Setting up the same problem as top and bottom. First, you would have to find the intersections, but you're going to, of course, want to find them in terms of x's. So intersection. We know these occur at y equals minus 1 and 2. So if x equals y squared, this means that your x would be equal to x equals y squared, and y squared equals 2. So this means that your x would be radical 2. Because I actually want to find this point here. X would actually be 4. And x would be, the other place I want is when it's -1. And so if I plug in y equals -1, so now in this idea here, I know that this is going to be at 1 is where this intersection happens. And this is going to be at 4, which is where that intersection happens. And there is a difference between being on the left of 1 versus on the right of 1. So on this side, we have our area is equal to the integral from 0 to 1 of the top function, which is going to be radical x, minus the bottom function, minus radical x. And then from this over here, you would have a equals from 1 up to 4 of the top function, which is radical x, minus the bottom function, which is going to be x minus 2. So this means that, let's call this A1 and A2. This means that your A is going to be the sum of these two integrals. And you'd have to compute two integrals to get to the answer, right? So sometimes just by changing your perspective, you can actually get an answer in a lot less time, like half the time, as opposed to here where it'll actually take longer. And this is where I'm also just using the fact that I knew some information before, and this is still going to take longer, even if I'm not even starting from scratch. So that might be something to consider about areas, that sometimes you can change your perspective. Just tilt your head to the right, and instead of top and bottom, think right and left, and that can actually save you a lot of work. Do I want to say anything else? Not really. Not really about areas. Okay, so now let's move on to distance and displacement. So this is also related to motion. We saw that maybe I should actually give definitions first. Distance traveled refers to the total distance covered by an object over some interval of time. This is different from displacement. Displacement refers to the total distance traveled by an object from some reference point. That's key. Over time. So let me show you an example. Let's say you have this object. Right, so that's what this guy is, object. Okay, this here is position 0. And it is our reference. Okay, so to say I pick a point in space and I'm like, that is my reference, that is position 0. And let's say the path, and this guy here is the path the object traveled. Okay, so let's say the object went to the right, and it went to the right by, say, uh, 10 meters. And then the object immediately turned around on a dime and went back. And it went past the reference point by 1 meter. Okay. Then in this scenario, what you can say is the displacement is -1, whereas, or the displacement is 1, whereas the distance traveled is 10 plus 11, which is actually 21 meters, right? So at the end of when I stop the clock, wherever that object is, I just measure how far is that from the initial reference point. I'm actually 1 meter from the initial reference point, but I didn't just move 1 meter. I went 10 meters in one direction and I came back 11 meters in the other direction. And so I ended up 1 meter from where I started, but it wasn't the total distance I traveled, right? Now, why would I care about displacement versus total distance traveled? Let's say I'm concerned about something like fuel consumption. It's a very different scenario to travel 1 meter versus 21 meters on some fixed amount of fuel, right? So I would want to know the difference between these two. Now, how would you go about actually computing these? So we saw that if S of t is a position function, and v of t is the velocity function, then the FTC gives a relationship between the two on a time interval at t in AB, let's say. From this, we can deduce distance traveled do displacement first. This is just going to be the integral from A to B of the velocity function, right? We saw that the position can be described as the integral of velocity. And if you want to know, oh, between this time and this time, where was my particle? I can just integrate from the initial position to the final position, right? What I want you to notice here is that the sign of your velocity can indicate direction. So for example, you can say positive means moving to the right, negative means moving to the left. And so when you're doing this integral and your velocity goes negative, it goes underneath the x-axis, we know about integration that that's going to give you return a negative value on your integral. And so you have these positive and negatives canceling each other out. And that's how you would get displacement. So it would act, in this case, it would give you a plus 10. And then for a part of it, it's going to give you a negative 11, because that's where the velocity would actually go underneath the x-axis. So that is actually displacement. Now you might say, well, how would I get total distance traveled? Well, we don't want the different directions to count against each other. So positive versus negative. You want it, for example, to always be positive. Always think of the absolute magnitude of the distance, right? So now distance traveled on AB. Well, that's just going to be take absolute values and keep everything positive, right? Even if we turn around and there's a sign change and it would subtract from the total distance that we moved, don't subtract, add it on to it. So don't take 10 and subtract 11, and so we get a difference of 1. Take the 10 and add the 11 that I traveled to it. So that's how I would get the 21. And so that's going to be the difference. Now, I don't want to waste too much time justifying that to you. Hopefully, me sort of just saying verbally some sort of justification can kind of convince you that this must be the case, especially when you take into account how integrals work and the relationship between position and velocity. But yeah, so let's do an example. A particle's velocity is given by v of t equals t squared minus 6t plus 5. Find A. Find its displacement from t equals 0 to t equals 3, b. Find its total distance traveled. From t equals 0 to t equals 3. See, for t in, say, 0 to 5, when is the particle moving forwards, backwards? When does it have max velocity or min velocity? Yeah. So, hint, consider the particle moving either as only being able to move either forwards or backwards, where forward is the positive direction. That means we're measuring positive distance. And backwards didn't say direction. And backwards is the negative direction. Okay. Then now we want to answer these questions here. Okay. So we know a velocity function for some object that's moving, and we consider forwards, or you can say to the right, means you're moving in a positive direction. Moving leftward, negative to the left, is going to be the negative direction. Yeah, want to do this. Between time equals 0, where t is time units. Between time equals 0 and time equals 3, what is the displacement? Between time equals 0 and time equals 3, what is the total distance traveled? Okay, so first, I would say displacement. First of all, we need to know where our v of t greater than 0 versus less than or equal to 0. Since the absolute value of v of t is going to be equal to, it's going to be v of t if v of t greater than 0, it's going to be 0 if v of t equal to 0, it's going to be negative v of t if v of t less than 0. We already know that. So we need to know where it hits 0, where it goes positive, where it goes negative. So v of t equals 0 means t squared minus 6t plus 5 equals 0. I think minus 3 minus 2 would work. This means that t equals 3 or t equals 2. I would plot this on a number line. And I mean, it's a quadratic, so you already kind of know, right? So you know that it actually looks like that, right? So you know that you're going to be positive over here. If you plug in a test value, you could plug in 4. You know you're going to be negative over here. You can plug in a test value, plug in 0. You know you're going to be positive over here if you plug in a test value like plug in a test value like 2.5. And then you're going to be negative, positive on that left side, 2.0. So you're positive. So v of t is positive for 0 to 2 and 3 onwards. And v of t is negative for t between 2 and 3. So now I can do A, displacement. That's going to be on 0 to 3. So I can do this from 0 to 3 of our t squared minus 6t plus 5 dt, but with absolute values around it. And this means whenever it goes negative, that's going to be an issue. So this means from 0 to 2, it is positive. So I leave the original v of t. And from 2 to 3, it's going to be negative. So you can do that. So that's t squared minus 6t plus 5 dt minus 2 to 3 t squared minus 6t plus 5 dt. And that should not be too much trouble, but I think I got as doing absolute values. I had done this earlier. So I think I got 23 over 3 here units, which you can check. And for B, I think I wrote this different. I did this the other way around. Let me just label it different here. So for A, this displacement would just be 0 to 3, and then I don't do any absolute values. So then it'll just combine the negative motion with the positive motion and just tell me the overall net change in motion. And so that's going to be 0 to 3 of t squared minus 6t plus 5. And I believe I got -3 here. So 3 units behind where it started. What else? For 0 to 5, when is the particle moving forwards or backwards? So C, on 0 to 5, I know from 0 to 2, I know over here it's positive, I know over here it's negative, I know over here it's positive. So it's moving forwards for t between 0 and 2, and t between 3 and 5. It's moving backwards for t in 2, 3. And I mean, it doesn't really matter if you use this as closed parentheses or open parentheses technically, but if its velocity is 0, it's not really moving. You can think of it as it just stopping for an instant. Max velocity. Min velocity. This is just finding the absolute max. So you would find critical points. This means v prime of t equals 0 or undefined. This means 2t minus 6 equals 0. This would mean t equals 3. So that's your critical point. So you're going to plug in v of 3. V of 3 is going to be 3 squared minus 6 times 3 plus 5. 9 minus 18 plus 5. That's going to be minus 4. 2 endpoints. So you're going to find v of 0. That's 5. And v of 5. And so that would be 0, I think. So it's 5 5s minus 6 5s minus plus 1 5. So max v on 0 to 5 is 5. And min v on 0 to 5 is minus 4. So those are just some examples. I just wanted to show you the difference between distance traveled and displacement. It's just a matter of, do you want to cancel out the negative direction versus the positive direction or not? So yeah, that's it. Now, I guess another application. So in terms of something you would be able to do, let's say if I threw a bonus problem on a final, it'll be a word problem just like this, where I'm just going to test you. Do you know the difference between distance traveled versus displacement? One, you're going to take absolute values. That's the one for distance traveled. One, you don't. So if you integrate the velocity function, that gives you displacement. If you integrate the absolute value of the velocity function, that gives you distance traveled. And you should know what it means to integrate the absolute value of a function. You just have to find where it's zero, where it's switched to positive, where it's negative, and you have to break the integral up into those intervals. Yeah. So there are a lot of concepts that we have done before that we're using here, but we're just applying it to a specific definition and a specific application. Here's another application that's pretty useful. Average value of a function. So remember, if y equals f of x is a function, then f of x the set of all f of x is the set of values of the function. Right, so values is just a set of outputs. Okay, so you have a function. Function is just doing its thing, right? So that's your f of x. Let's say you care about on some interval a, b, and all of these guys will give you some values. So let's say I call a, as usual, x like x0, call this like xn, and I can have a bunch of x's in here, x1, x2, x3, and so on. So I would have f of x1, f of x2, f of x3, going all the way up to blah, 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 f of xn, right? So these guys here are all the values. And I want you to note something in particular. Note there is an infinite number of them. So the question is, what if we were interested in, on average, what is the output of this function, right? So let's say for some reason, I had to guess without really knowing what the input is going to be. If someone were to say, oh, I'm going to plug in some random input and get an output from this function, what do you guess the output is going to be roughly, right? And I know that seems like a weird question to ask, but questions like that would come up in probability all the time. There are times when we want to be able to make predictions and we want to know on average what's going to happen, right? Like if I were to do this experiment 1,000,000 times on average, what would be the outcome, right? So that's the kind of situation we want to describe here. So we have all these values and we want to know what is the average of these values in terms of the mean average, right? So the question would be, what is the average and I'm talking about mean how to spell average. Mean value of the function on AB. So of course you'd recall what the mean is. The mean of n values, say x1, x2, all the way up to xn, is given by you add all of them together, and then you divide by the number of them that there are, right? So that is the mean, right? Oftentimes we call this x bar, right? So in a statistics context. So we want to compute a measure like the above for the f of x's, right? So that's what we want to do, right? So how do you actually go about doing that? Well, take a sample. So we're going to have A to B. So, you know, like we have our x0, our x1, our x2, our x3, etc. Again, each of these is like delta x in terms of just our normal thing. And recall our delta x equals b minus a over n. And this, of course, would mean that our n is equal to b minus a over delta x. Now, we're going to use that at some point. And take the corresponding outputs. So I want to take like f of x1, f of x2, all the way down to f of xn, and find the mean. Then this means the mean f of x of this sample is going to be, you know, f of x1 plus f of x2 plus dot 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 f of xn all over n, right? But we now know from above that our n is b minus a over delta x. So this ends up being f of x1 plus f of x2 plus da 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 plus f of xn. You know, the flip and multiply, we would get this. And notice that this is kind of like the sum. I goes from 1 up to n of f of xi times delta x all over b minus a. And that should start looking familiar to you. So to get all values, let n approach infinity. So this means that the average of all values on AB, let me call that f sub average. That's just going to be the limit as n approaches infinity of this guy. But by definition, that is like the integral. So this leads to a formula for the average value of a function. So this leads to the fact that f average is going to be 1 over b minus a times the integral from a to b of our function. And that's that. This is a way to compute the average of an infinite number of values. You can actually use an integration. Integration you can think of as, remember, it's essentially like a Riemann sum where you're summing stuff up, but on steroids. It's like you're going from a sum where you're counting discrete values to continuous values. It's like an infinite sum, like on steroids. So that's what an integral is. So an integral is a way of adding up a bunch of things very, very efficiently. That's one way you can actually think of it. So an example here, I could say find the average value of f of x equals x squared, let's say, on 0 to 2, right? So I have y equals x squared. And I care about being on 0 to 2. So the question is, on this interval, what is the average output, right? If I were to take all the outputs here, right? So I'm going to get some numbers here on the y-axis. If I were to imagine that I could take all those outputs and tell you, on average, what would the output be? What is it going to be around, roughly? And give you an answer, what would that be? Here, we would simply go with the formula. The average output would be the integral from 1 over b minus a times integral from a to b of our function. This is going to be 1 over 2 minus 0, integral from 0 to 2 of x squared. It's going to be 1/2 times x cubed over 3, between 0 and 2. And that's going to be 1/2 times 8 over 3, or 4 over 3. So that's roughly, 4.333. That's the average output on that function. Now, notice that the outputs range from, on the high end, you can get up to 4 as the output. On the low end, you're getting 0. But you're getting a bunch of values in between 0 and 4. So the thing is, you're getting a bunch of numbers being outputted, and you want to find their average. You know that they're between 0 and 4, and they come, and the output is coming from x squared. What is it going to be roughly? Turns out 4 over 3 is going to be the average value. The average number of values will be closer to 0 than to 4, right? So would I guess that if someone were to tell me, well, what do you think the chances are that if I throw a random value between 0 and 2 into y equals x squared, that the output is going to be like close to 4, like 3.999 or something like that? I would say there's like a 60% chance that that's not going to happen. Like I'd be able to know roughly on average how often such a thing would occur. And I would be right about 67% of the time. So that's cool. That's the average value of a function. Another thing that we have, another application, is the mean value theorem for integrals. So we have a mean value theorem for derivatives. It says that you have a continuous function on AB. It's continuous on the closed interval AB. It's differentiable on the open interval AB. Then there must be a point in the interior in between A and B such that the derivative of that point is equal to the average rate of change over the interval. The mean value theorem is very similar, but it says that there is a point in the middle assuming your function is integrable on AB, such that there's a point in the middle such that the value at that point is the average value. You will be able to find. So the average value is going to be somewhere in between 0. The input that gives you the average value is going to be somewhere between 0 and 2. Let me state that specifically. Mean value theorem for integrals. Suppose f of x is continuous on AB and integrable on AB, then there is some C in AB such that the output at C is equal to the average value of the function as defined by that. Okay, that's all that is. Example. F of x equals x squared on 0, 2 satisfy the assumptions. It is continuous on 0 to 2, and it is integral on 0 to 2, right? We know that the integral is x cubed over 3 plus c everywhere on that interval of the mean value theorem for integrals. Find the c that satisfies the conclusion. So the idea is we want C so that f of C equals the average value. This means we want C squared equals, we computed that to be 4 over 9. So I can just solve for C. So C is going to be plus or minus 2 over add 3. Minus 2 over add 3 is not in the interval. It's not in 0 to 2, so reject. And C equals 2 over add 3 satisfies the conclusion. Right? That guy's definitely less than 2, and it's still positive, so it's bigger than 0. It's definitely in 0 to 2. So that's that. So those are all the other applications I wanted to talk about. So in terms of areas, we have the top minus bottom idea, and that's the one I'm going to test you on. However, I just want you to start appreciating the fact that not everything is top and bottom. Some things are left and right. And when you get to calculus 3, it's not only going to be top and bottom and left and right either. Right? You're going to have to all sorts of directions to contend with. So you can tilt your head to the side, think of things in terms of y than in terms of x. And there are cases where it might make your life easier, where we can do one integral as opposed to having to do two integrals. Distance and displacement is another application. Distance is the total distance travel is the integral of the absolute value of velocity over the interval that you care about. And displacement, meaning how far did this thing move from the time where I started measuring its motion? And just between the initial position, how far away from that initial position is it? That's called displacement. And that is just the integral of velocity over the interval. So we just did that. Then we looked at the average value of a function. That's just what is the mean average output on some interval, right? If I had to guess, or if I look at the outputs of a function as just a bunch of numbers, what would the average of those numbers be? If I added up all those numbers and divided by the number of numbers there were, if it were possible for me to do that, what answer would I get? And it turns out that the answer you would get is given by this formula. It's given by an integral formula. And you can actually guess, you can actually figure out what input would give us that output. And it turns out that there's a theorem that says the input would have to be in the original interval. And you can actually compute it by just solving this equation. So those are the examples. They're nice examples to know, especially the average value of a function. That actually can come in handy soon. Displacement and distance and displacement, I guess you would mostly encounter that in like a physics context. But the average value is a much more general thing. Encountering the mean, the mean value theorem for integrals, I don't think one would encounter that very often, but maybe in any case where you would encounter the average value of a function, that might also come in handy. But personally, I haven't encountered that very often. But the average value is actually something super important. Finding the mean in more general terms is a super important pursuit. So for now, we'll stop there. We'll take a small break, 10 minutes, maybe a little less, and we're going to start something that I think it's fun. It's going to be not as, there's this theory of this and blah. It's just going to be, here's a technique to compute stuff and kill integrals, which, I kind of like that stuff. So we're going to do integration by parts when we return, and we're going to wrap it up there. You kind of know what to expect from the final exam. So not much more to say on that. What I would remind you is that probably the best practice is the old finals that I have in the class, on the class website. Best practice is going over the old finals on the class webpage. I would say for extra practice, look at homework problems. So I know some of the homework problems went up late, so I'm not going to count the entire sets of homework towards your grade. I'll probably only do like chapters 1, maybe a little bit of 2, the ones that I got posted early. However, I still think you can look through the homework for just extra problems. So say you practice all the final exams that are on the class website, right? But you still realize that with this topic, I'm still kind of, I'm not that great. Like I got the same problem wrong every single time I did a final, right? And you want extra practice on that topic, I would just like go through some of the homework problems for that topic. So you can use those to help you study as well. That's probably how I would use all the homeworks that were put up recently. But that being said, to get the feel for what you'd have to be able to do, I think the best thing that would give you that feel is going to be going over the old finals on the class website, as well as what it would actually feel like to do it. It's going to feel like test 1 and test 2 pretty much, right? So in terms of the feeling of taking it, it's going to feel like test 1 and test 2, just a little bit longer. In terms of what you would need to know to do well, I would use the old final exams as a guide. So that being said, we will take a break here, and we'll return and do some integration by parts, which should be interesting. So I'll see you guys in about 10.
The show will start in 9 minutes. The show will start in 8 minutes. The show will start in 7 minutes. The show will start in 6 minutes. The show will start in 5 minutes. The show will start in 4 minutes. The show will start in 3 minutes. The show will start in 2 minutes. The show will start in 1 minute. And now, on with the show.
Okay, and we're back. Let's actually get through some exciting stuff. At least I think so. Integration by parts. So I typed up some of this stuff because I wanted to focus on the mechanics as opposed to writing out too much of the steps that you would have to go through. So yeah, let's do that. So here we are with integration by parts, which is going to be the reverse of the product rule. And let's see like how that would work. So recall the product rule. This seems a little bit too big here. Recall the product rule. What did the product rule say? Well, it said that the derivative of one function times another is going to be equal to the derivative of the first times second plus first times the derivative of the second. Okay. Now, FTC, fundamental theorem of calculus. Remember what this implies to us. Derivatives and integrals, they're sort of inverse operations of each other. I can kind of use one to undo the other in some sense. I just need to make sure that if I'm using an integral to undo a derivative, there's going to be a plus c that comes up. Okay, so other than that, they're pretty much inverse operations for the most part. And so what we can do is instead of thinking of this as a derivative formula, try to figure out an integration formula for it. So what we can do is we can take integrals of both sides. Integral distribute across sums. So on the right side, I get an integral sign before each of them. Now the fundamental theorem of calculus is going to tell me that the integral and the derivative are going to essentially cancel out. And so this is going to give us that f times g is going to be the integral of f prime times g plus integral of f times g prime. And I'm going to choose one of these arbitrarily to solve for. So let's say I solve for f times g prime. So this is going to be, of course, technically there's a dx here when you start integrating, right? So dx. I don't want to write that in right now. Don't want to confuse things. So we have f times g prime. The integral of f times g prime. I'm going to take the other integral, move it to the side where the f and g are. So that's going to leave me with f times g minus the integral of f times g, f prime times g. Okay. So now what we normally do customarily, let's do a change of notation. Set u equals to f of x and v equals to g of x. This means that du is going to be f prime of x dx and dv is going to be g prime of x dx. And so the above can be written as the following. The integral of u dv, right? Because g prime dx is going to be dv just by the differential, is equal to u times v minus the integral of v du. And that, ladies and gentlemen, is our formula. This is called the integration by parts formula. And why is it called integration by parts? Because we are going to be choosing parts. The parts are u and dv are parts of an integral that will be chosen. Right? So it's called integration by parts. That's because you're thinking of this as two functions, two parts, an f and a g prime. You're going to choose the f to be a u. You're going to choose the g prime to be the dv. So you're choosing these parts, and you have this integral formula. The idea being, so the main idea here is, and you're going to see how this works out in some sense in a few examples. The main idea, we want to compute the integral of, say, u dv, but it may be easier to compute the right side, u times v minus the integral of v du. And let's actually do some examples. Right, but that's the integration by parts formula right here. Okay, and essentially what it is was I took the product rule, I integrated both sides of the product rule, move things around in the equation, and I got this integral equation, which at first it looks complicated. Like I went from an integral on the left side to like two things on the right side, but it turns out that by doing that, sometimes you can actually figure out how to integrate something that you couldn't before. So let's actually look at a guy like this. Now, so we're going to look at the example like x e to the x. Now, as I mentioned here, I do want you to remember the strategy. So one is you try to apply a basic rule. Does that work or does that not work? Two, simplify to use a basic rule. And three, you would think substitution. Now, it turns out when you do this, none of these are going to work. They won't work, including substitution. So substitution would actually lead you to another integral that we don't yet know how to do. Substitution, you might think, so maybe like u equals e to the x would be a substitution, in which case you could get that ln of u equals x. So this means that 1 over u du is equal to dx. And so you would have to actually integrate ln u times e to the x times dx, which is 1 over u du. So you'd have to have the integral of ln of u du. And that, we actually don't know how to integrate ln. So obviously, it's like when I first asked this question, oh, what's the integral of ln? They'll tell me 1 over x, but it's not 1 over x. The derivative of ln is 1 over x. The integral of ln x, we don't actually know. That's not a basic rule for us. Not yet, anyway. Once you learn about integration by parts, that's where we're going to figure out how to integrate ln of u, and then it's going to be a basic rule after that. So none of these guys work. So now you might have a fourth step by parts. And there will be reasons why we will choose this. There will be specific indicators for this. But in this class, I'll either tell you when to use it, or you should notice none of steps 1 to 3 work. Now, there are some giveaways for integration by parts, things like 2 different types of functions being multiplied together. Like here, we have an x and an e to the x, right? So it's a polynomial times an exponential. There are times when you might have a single function, but it would be more convenient to have the derivative of that function as opposed to the original function. There are other times when you might have 2 of the same types of function, but integration by parts is just something you try and win because you know it's a pattern. Integration gets a lot more complicated, as I'm trying to say. It's not as straightforward as derivatives where, oh, I see 2 functions multiplying, it's the product rule. It's always the product rule. It's not true for integration. It could be a substitution, could be an integration by parts, could be a bunch of things. You just have to look for certain patterns. But we see an integral in this class. I definitely want you to think of these 3 things first. But if none of those work, then it means you're in the bonus section of the exam. And this is the only other game in town. So you would use that. So how would this actually work? So we would choose to use int by parts here. Now that you know to choose that you want to use integration by parts, how do you get the parts? So that's going to be the first one. You want to choose the parts. The parts you're going to choose are u and dv. So you have 2 functions here, like an x and an e to the x. You're going to choose one to be a u and one to be a dv, essentially. And so here, let's do this. I have x e to the x. I'm going to let u be x and let my dv be e to the x dx. Okay. Now what I'm going to do is I need to find the other side of the formula. So once I have my u and dv, I need to find the v and the du as well. So that's what I'm going to do. This means that du is equal to dx. And what I did here was differentiate. And then this means that my v would be e to the x, right? And here I integrated. So now notice that I have my u, my du, my v, and my dv. I have all the parts from the integration by parts formula. And I start by choosing the parts. So these guys here, were chosen. Yeah, so you'll choose the parts. Then you would find the other 2 parts that you need by differentiating and integrating. And then you're going to plug into the integration by parts formula. So this is going to be something I'm going to be doing later on. Let's say I said I equals this. So my I is equal to the integral of x e to the x dx. And I chose x to be my u. Right, so x is my u, and so that's this part, and my e to the x dx is my dv. Now this is supposed to give me on this side u times v minus the integral of v du, and I'm going to simply just plug those guys in, and I need to like move these guys over. Okay, so it's u times v, my u is x. My v is e to the x minus the integral of my v, which is e to the x. My du is just dx. So you'll have that. Now, once you get to this part, you now compute the integral on the right by applying general integration strategy. You'll notice here, in this case in particular, the integral on the right is easier to deal with than the original integral. That's just the integral of e to the x dx, which there's a basic rule for that, right? So here, you do this again. Go through this process again. So you're going to get a new integration on the right, which is, in this case, it's this guy. And you're just going to start over. You're going to look at it and be like, well, is that, can I use a basic rule for this? Can I simplify to use a basic rule? Can I do a substitution now? Will integration by parts work? You go through the process again, right? The idea is the integral on the right should be easier to deal with than the integral on the left. And in this case, it is, because you'll notice that here, a basic rule can deal with this guy. It's the basic rule. That's one of the guys we have memorized. So this is going to be x e to the x minus e to the x plus c. And that's going to be your answer. And of course, you can check this in case you don't believe me. If I were to take d dx of x e to the x minus e to the x plus c, what would happen? I would do the product rule. Derivative of x is 1, leave the e to the x, plus leave the x, differentiate the e to the x, minus derivative of e to the x is e to the x, plus 0. This guy would die, that guy would die, and you would just be left with x e to the x. Which is the original integrand, x e to the x. Yeah, so that's actually the integral. So it wasn't a basic rule. I couldn't simplify it to a basic rule. What am I going to do with x e to the x? Can't really do anything. Substitution, it's not going to work. U equals x is always the bad substitution. So the only other thing I could substitute is e to the x. But if I substituted e to the x, I would end up with integral of ln of u. What is that?
We don't know. We're going to know. But now, so that's just a run through. And again, I do a lot of like explaining while I'm going through the problem the first time. The others, I'm going to do it a lot quicker, and you're going to see it more clearly as I move on. But a question that would come up at this point, I think, a very reasonable question is, well, how do you choose the parts? Because things could have gone very differently if I went the other way, right? So I just actually want to deal with that. Notice what would happen if I chose the parts differently. So let's say I had x e to the x. I realize, okay, nothing that we've done before can work on this guy, so it has to be an integration by parts. Let's do it. And you go, I should put this in red because it would be a bad choice, and I want to show you why it's going to be a bad choice. Let u equals e to the x instead, and let my dv equals x dx. Now, this would mean that if I differentiate it to get the du, that's going to be e to the x dx. Whereas this time, if I integrate to get the v, that's going to give me x squared over 2. Now, when I go to plug into the formula, it's going to be u times v minus the integral of v du. And v du would be, well, x squared over 2 times e to the x dx. In other words, I have now x squared over 2 e to the x minus 1/2 x squared e to the x dx. Now, what you notice about this guy is he's worse than the original integral. Before, I only had an x times e to the x. Now I have an x squared times e to the x. I literally just made it more complicated. There's no way that was the right move, right? So there is such a thing as making a bad choice here, choosing the parts in an incorrect way. So you're going to want to know, well, how would you choose the parts? And there is a guideline that goes along with this. So let's say how to choose. So there's a mnemonic for when we have two different classes of functions. And the mnemonic is, there are a couple ways that people call this. Liate is one of them. Liate. And liate is just a mnemonic for the type of function that we have. So this is log. This is inverse functions. This is algebraic. Well, it's called algebra. Either way, it's a misnomer. It really means polynomial. T stands for trig function, and E stands for exponential. So these are the 5 classes of function that we can have. Now, here's how the choice is made. guys higher in the list get to be U first, right? And then guys lower in the list gets to be U last. Another way to think about this, because Liate is weird, and you don't want to, some people just didn't like the fact that they use algebraic or algebra as a part of the mnemonic. So they created a new one called Lipit. Or, because to put polynomial in there, Lipit would sound very weird, as well as whether you chose the trig function or the exponential is not that important. Like these guys can be switched. Without too much consequence. So instead, some people think of it as Lipit, which again, this stands for logs. This stands for inverse functions. This stands for polynomial. This stands for exponential. This stands for trig. By far, I would say, though, that this guy here, Liate, is more popular. So I would say know this as the mnemonic. Know Liate as the mnemonic for choosing the parts. So this is why given the integral x e to the x dx, what I noticed here was that the x falls under the A category, while the e to the x falls under the E category. A is higher in the list than E. Right? Because in Liate, the A comes before the E. Right? So your A is higher in the list than E. So the A gets to be the U. And then that's where we come down and so that's where we come down and we're like, okay, let U equals the X and dV equals the E to the X, right? Because according to Liate, the A would come before the E, therefore the A is going to be my U. And this is really just a mnemonic. It's just that people tried a bunch of different combinations when these guys show up together, and this was found to be the best way to actually tackle it when several problems several types of functions are attached together. So if you're thinking of doing integration by parts and you have two functions being multiplied together and you have to choose the parts, you would choose them according to Liate. So if you have a logarithm times a polynomial, the logarithm gets to be the U. If you have an inverse trigonometric function times the polynomial, the inverse trig function gets to be the U. If you have a logarithm times a trig function, the logarithm gets to be the U. If you have a polynomial times a trig function, the polynomial gets to be the U, etc. Right? So you always have this kind of idea. Yeah. So that's how you choose. So let's just do a few more examples. So say you have this one, x squared times ln x. Okay. Now, again, every single time, all the time, and this is going to help you a lot in Calc 2 as well. Don't just think of approaching any integral completely randomly. In fact, don't think of anything like that. Like even with limits in this class, I gave you guys a strategy, what to look at first, second, third. You want some kind of heuristical approach to a lot of mathematics, because otherwise you just end up lost. You're running around like a chicken with your head cut off. You don't want to be that way. You want to just know, I'm facing this problem. There's a certain way to think about this problem that has been tried and tested for centuries before I was here. If there was a better way, we would have found it by now. This is how we're doing it, right? And I guess that's not true in general. I mean, you do have people figuring out new ways to do things sometimes, but you know what I mean. Like if you're going to be the person who's going to invent a new, faster way to do something that no one's thought about in centuries, then chances are you're not the kind of person I would be giving this advice to in the first place. Chances are you'd probably already have your PhD or something already. Okay, so let's move on. So you want a strategy. So every time you see a new integral, you go through this step-by-step system in your head. Is it a basic rule? Can I simplify it to look like a basic rule? Will substitution work? You always think those three things first, every single time. Now, beyond that, there's no set order in which you think things, but you think about applying a strategy based on the pattern within the problem. So one pattern is you have two different types of functions multiplying each other. Then integration by parts starts to become something that you would think about. And again, that's assuming substitution doesn't work, because yesterday with substitution, we saw situations where we had two different types of functions multiplying each other, like x squared times the radical of 1 plus x cubed, right? Those are two different, that's a radical function times a polynomial. I would not do integration by parts there because substitution would work, and substitution is step 3. Integration by parts would be step 4, right? So I'm not going to do an integration by parts. Other than that, once you know substitution or nothing easier would work, and you have two different types of functions multiplying each other, integration by parts would be a good guess as to what you should do in order to solve the problem. So here, you'll notice that what I have is x squared, this is an a, ln x, this is an L. According to Liate, this guy gets to be the U. And so then we can actually proceed on doing that. So how do you do this integral? Let U equals ln x. Let dv equals x squared. So du would be 1 over x. V would be x cubed. Well, you should add the dx here. X cubed over 3. And so this means I, let's call this I. I'll call it I when I just don't want to bother writing out the original integral. I is equal to, you don't have to write this, but u times v minus the integral of v du. So that's u times v, that's x cubed over 3 ln x, minus the integral of v du. All right, so that's going to be x cubed over 3 ln x minus, this is just 1/3, the x's are going to cancel, that's x squared. And now, again, you now have a new integral. Go through the integral strategy in your head again. Of course, step 1 takes care of this. It's a basic rule. It's an integral of x to the n. We know how to deal with that. So you're going to add 1 to the power and divide by the new power, plus c. So then you have x cubed over 3 ln x minus x cubed over 9 plus c. And that's going to be the integral of x squared times ln x. Okay. Right. So that's cool. Let's actually do another one. Again, you'd go through the integration strategy in your head. Is this a basic rule? Can I simplify to a basic rule? Can a substitution work? The answer to all of these questions would be no. We're in Calc 1, and the only other thing Jhevon taught us is integration by parts, so that's got to be it. All right, so now we will jump into integration by parts. We're going to need to choose the parts. This guy is an E. This guy is a T. Liate, E comes after the T, so the T gets to be the U. You would go in and say let U equals the sine of X. dv equals e to the x dx. Your du is going to be cosine of x. Your v is going to be e to the x. I will call this I just because I'm lazy. And so this means that I is equal to u times v minus the integral of v du. So we need another integral. We go through the strategy again. Is this a basic rule? Can I simplify it to be a basic rule? Can substitution work? In fact, you can kind of see that the answer to all of those would be no. It's very similar to what the integral was before. You just have now a cosine instead of a sine. And so what you would do is like, int by parts again. So what we're going to do is int by parts again. Liate, let u equals the cosine, v equals dv equals e to the x dx. Then your du would be minus sine of x. Your v would be e to the x. And so I'm going to do integration by parts again inside these parentheses. U times v minus the integral of v du is going to be a plus sine x here. And so now you have a new integral and you're going to be like, all right, so we want to do this guy. And something you're going to realize about that guy is that that's actually the original integral. So you might think int by parts again. Well, no, you'd be going forever, right? Because you're going to just go back to the e to the x cosine, then back to the e to the x sine, then back to the e to the x cosine, then back to the e to the x sine. So yeah, I guess integration by parts can't deal with this guy. Well, no, of course it can. That's why I put it as an example. But you don't do this, you'd go forever. The solution here is to just realize it is now just an algebra problem. Notice that what we have is that we have an equation where the thing we want to solve for is on both sides of the equation, right? This is really just I, right? So in other words, I have I is equal to e to the x sine of x minus e to the x cosine of x minus I. And so what I can do is I can move over here, add I to both sides. And then divide both sides by 2. And of course, the plus c comes from the constant of integration. So yeah, we can still solve for that guy. So there is such a thing as an integration by parts that kind of revolves on itself. And this usually happens when you have like an exponential and a trig function, because the trig functions, especially sines and cosines, they kind of give you back the same thing eventually. And so you can end up with the same thing over and over. And the way out of that loop is to just stop at the point where you get the original guy back and just treat it as an algebra equation and isolate the guy you want on the same side of the equation. So yeah, that's how you would do that. Let's do another example. Let's do x cubed e to the x. Find the antiderivative of that. So again, is it a basic rule? Can I simplify it to be a basic rule? Does substitution work? The answer is going to be no. You're going to be like, okay, so integration by parts. So you're going to go in. That's an A. That's an E. Liotte says the A should be the U. So here I would let U equals x cubed, dv equals e to the x dx. This means that my du is going to be 3x squared dx. My v is going to be e to the x. Call this I. This implies I is equal to u times v minus the integral of v du. Now I have a new integral to consider. All right, so it's again integration by parts. Hopefully you notice that. So I'm going to again go in and be like, okay, u equals x squared, dv is equal to e to the x dx, du is going to be 2x dx, v is going to be e to the x. So this is going to be x cubed e to the x minus 3 times u times v minus the integral of v du. Get a new integral. So again, an integration by parts. All right, but notice that we're progressively getting better here. We had an x cubed e to the x, then we went down to an x squared e to the x, then went down to an x e to the x. We actually know how to do x e to the x. We actually did that as an earlier example. So we know that we're at the last step. Let's just finish strong. U equals x, dv equals e to the x dx. This means that your du is going to be dx and your v is going to be e to the x. So you're going to plug that in. This x cubed e to the x minus 3 times x squared e to the x minus 2 times all these nested parentheses, u times v minus the integral of v du. I had a friend a long time ago that told me he remembers it by the word video, like so VDU. That's how, for whatever reason, he remembers this formula. But however you remember it, I don't particularly care. Just make sure you remember it. But this is now a basic rule. You know how to integrate that. That's just e to the x plus c. So here you'd have x cubed e to the x minus 3 times x squared e to the x minus 2 times x e to the x minus e to the x plus c. And you can actually expand all this. So this is going to be, say, x cubed e to the x minus 3x squared e to the x plus 6x e to the x minus 6 to the x plus c. Whew. And that one took a long time. And so you might think, well, that one, like 2 integration by parts, nested parentheses. Man, that's got to be the longest integration by parts problem that Jhevon would give us, right? So there's no way you'd go worse than that. But then this is going to be the following example. X to the 5th, e to the x. And at this point, you would see that guy and you would be like, all right, you start crooking your neck, you start, stretching out your fingers, you start getting yourself ready. And then you go like, nah, not doing that. Gotta be a better way, right? And unfortunately there isn't. You have to kind of bite the bullet. I'm kidding. Of course there's a better way. Yes, of course. Right, I mean, clearly you should sort of notice that there's a pattern here with the nested parentheses, and you know what formula is going inside each parentheses. You can kind of multiply it out and come up with some general formula. And that way you can kind of streamline integration by parts. There is a way to streamline multiple integration by parts. And it's called tabular integration. Now it's called tabular integration because you kind of do it in a table to organize your work. And so that leads us into tabular integration. So let me quickly describe, quote unquote, tabular integration. Thank goodness I kind of retyped some of this stuff. All right. So let me describe to you how this guy is going to work. So tabular integration. Suppose you wanted to do an integral that's like big F times big G dx, right? And you want to use integration by parts where you would set the U equals to the big F and your dV would be the big G, right? So I'm going to use F prime, F double prime to be like a repeated differentiation of the U function. And I'm going to use G sub 1, G sub 2, G sub n to be repeated integration of the G function. So me finding V after every time I choose dV. And so there is a way that you can actually line this up. So in a table, so I would have, say, big F times big G dx. And here's how the process is going to work. So this guy is going to be my U. And this guy here is going to be my dV. I'm going to line it up so that the U is on the left and the dV is on the right, just so it kind of looks nice. And I'm actually going to create a table below this integral. Where I'm going to actually perform both operations. So in the first column with the F, I'm going to just keep differentiating. Differentiate. Just keep going, right? So this here would be F prime, this here would be F double prime, this here would be F triple prime, etc. And I keep going until I take n derivatives. Okay. Now you might wonder, well, how long do I have to keep going for? But we'll get to that. And then for the G, you're going to keep integrating. So I'm going to have the first integral, the second integral, the third integral, and then I'm going to end up integrating n times here, right? And so what we're doing is keep differentiating in the left column. Keep integrating in the right column. And so that's the first thing, right? Now what we're going to do is we're going to multiply in a specific pattern that I'm going to show you. So what you're going to do here is you're going to multiply along the diagonals as shown by the blue arrows, and apply the indicated sign. So here's what you would do. You would take the big F times the G1, and the F prime times G2, F double prime times G3, F triple prime times G4, etc. You're going to keep going until you go down here. And then finally, along that line, along the last line, you're actually going to multiply in this direction. And the signs are going to go as follows. You apply a plus sign to the first multiplication, negative, positive, negative, etc. Like, you don't really know what this is going to end up being. But by the time you get here, you're going to have some sign plus or minus, depending on whether you did this an even number of times or an odd number of times. And of course, before that, you had to have a minus or a plus. And you have this pattern. And what you would do is for the last red arrow, you will integrate the product. And so what you're going to do is you're going to get a list of expressions that look like this, right? So you're going to end up with, now describing it is going to look, I'm pretty sure it might already be complicated, but once in practice, once you get used to it, it won't be so bad. So what you're going to have is you're going to have F times G1 minus F prime times G2 plus F double prime times G3 minus F triple prime times G4 plus ... right? Now, there's going to come a point just before the last row where it's going to be like minus plus F to the n minus first derivative times G to the nth derivative. And then finally, you're going to end with this red arrow where it's like plus minus the integral of F to the n times G sub n, right? And this is ultimately the formula. This is a generalized integration by parts, which we can streamline via the table, right? So it turns out that that's like integration by parts in its most general form, right? So this is like the table is our mnemonic device. And hence, that's why it's called tabular integration, because you kind of use a table. Now, you might have a concern. How big does the table have to be? I'm glad you asked, proverbial student. Here is the important thing you want to know. When does the table stop? How do you know to stop building up this table? Well, it's when one of three conditions are fulfilled, any one of three conditions. So either the derivative column eventually hits 0, which would of course happen if you have a polynomial, right? Like an x cubed becomes 3x squared, becomes 6x, becomes 6, becomes 0. Like it'll eventually hit 0. That's one condition. And then you stop the table at that point. Another condition is that you keep doing it until you get a row that you realize, hey, if I multiply it across, that's actually easy to integrate. I could just stop now arbitrarily because I know how to deal with this particular integral. And then that would actually work. The third thing is whenever you end up with a row that becomes a constant multiple of the original, right? And this is what would happen in like an e to the x sine of x situation. Eventually you're going to get to a row where it's a constant times e to the x sine of x would be the result. Perhaps 1 is a constant. You'll get exactly the row back. But yeah, and ultimately you'd actually get like, you'd use this extend integration by parts formula. So that's the general formula. So here, what I'm going to do is I'm going to repeat this. I'm going to repeat a bunch of them with tabular integration, a bunch of situations like x cubed e to the x, x squared ln x. Everything that we've done before can still work with tabular integration because it's really just a generalizing integration by parts, just streamlined. So what you can do here is you can build a table. Keep differentiating the x cubed, 3x squared. Maybe I should write it in green to kind of match the picture I had above. So you build a table. Start differentiating 3x squared, 6x, 6, 0. You see that 0, you stop. Condition 1, right? So you stop. You go to the other one, you keep integrating. E to the x, this one is easy. Then you multiply down the diagonals. So it's x cubed times e to the x, this times this, this times this, this times this, this times that. So it's plus this, minus that, plus this, minus that, plus this. So it turns out that this guy is going to be equal to plus x cubed e to the x minus 3x squared e to the x plus 6x e to the x minus 6e to the x plus the integral of 0, which of course is just your plus c, right? So the integral of 0 is just a constant, right? Because the antiderivative of 0 is a constant, because if you differentiate a constant, you would get 0. So yeah, that gives you, you'll notice that that gives you the same answer as before. Right? If you look back at what we did up here, x cubed e to the x, notice how we got that same guy, x cubed e to the x minus 3x squared plus 6x minus 6, blah, blah, blah. All of that showed up here. What about this one? X squared ln x. You can still do this. The first thing you would do is actually rewrite it in another order, because I want my u on this side and my dv on that side. I would have a table. Differentiate the ln. That's 1 over x. Integrate this guy, x cubed over 3. And at this point, I would actually stop. Stop. Condition 2. If I multiply across, that literally just gives me a polynomial, right? So I would go this times this with a positive sign, that times that with a negative sign. And so ultimately, this becomes x cubed over 3 ln x minus the integral of 1 over x times x cubed over 3. Right? You get the integration by parts formula if you just stop tabular integration at the first row, at the first newly created row. So yeah, so you again get the answer, x cubed over 3 ln x minus x cubed plus c. What about that one with the repeated integration by parts? I think was the next one. Let's actually do that. Tabular integration can deal with that as well. So again, I would go in, do my table. Actually, it doesn't matter who I do first here. So I can differentiate the e. Well, I can differentiate the e to the x. Let me switch it just so it matches up nicer with the previous thing. So differentiate sine, I get cosine. Differentiate cosine, I get minus sine. Integrate e to the x, I get e to the x. Integrate e to the x, I get e to the x. This line here, you'll notice is I would get minus e to the x sine x. This is a constant times the original integrand. Right? So that's a constant times that. I have a minus 1 times that row. So at this point, you stop. Ooh. I don't know if you guys heard the thunder. Yeah, accidentally. Okay, so I would continue. This times this, positive sign, this times this, negative sign, this times this, positive sign. So this would give me e to the x sine of x minus e to the x cosine of x plus an integral of minus sine x times e to the x dx. So that would mean that my integral is going to be equal to this guy minus the original. So again, I get 2I equals this. And so my I is equal to half of that. So we get that again. So tabular integration can handle integration by parts generally in any case that you end up with, because it's just a way to generalize your integration by parts. Now, we can go back and do this guy, the x to the fifth e to the x, which seemed like it would be a horrible idea, but it's actually not so bad now that we are equipped with tabular integration. What I would do is just differentiate. I get 5x to the fourth, 20x cubed, 60x squared, 120x, 120, and eventually I would hit 0. Now at that point, stop. Condition 1, right? Then the e to the x, I'm just going to keep integrating. So that's e to the x, 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 e to the x. And I'm going to multiply this times that, 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 this times that. Plus sign here, minus sign here, plus sign here, minus sign here, plus sign here, minus sign here, plus sign here, which is going to be a 0. That's going to be a plus c when I integrate. So I can just go in. All right, so that's x to the fifth, e to the x, minus 5x to the fourth, e to the x, plus 20x cubed, e to the x, minus 60x squared, e to the x, plus 120x, e to the x, minus 120 e to the x, plus c. And that's my integral. Yeah, so that's integration by parts. I taught you integration by parts as well as how to streamline it with tabular integration in case you have to do it repeatedly. But technically, you could always do tabular integration as a mnemonic device, because the integration by parts form that I derived for you at the beginning of this section is just if you stop tabular integration after one row, right? But you might want to do several rows depending on the problem. So I would say you should try a couple more. So with more examples, you can try these. Maybe what I'll actually do is, I'm not going to do all of these, but maybe I might just do a few of them. And what I can do is I can write up the solutions for the others, and you can just look at them, I guess, see if you understand. But at least F I want to do, and maybe I'll just do a couple of the others for fun. Because F is like the integral of ln x, right? It's something that would be nice to know. It's not something that they expect you to know at the end of a Calc 1 course, but hey, if you show up in Calc 2 and your professor, anyone knows what the integral of ln x is? Because he expects to catch you, because there's going to be a bunch of students that are going to say 1 over x, because they're not paying attention to their formulas, like Jhevon told you to pay attention to your formulas. And so a bunch of them will say 1 over x, and then the professor is going to, that's not true. You're not paying attention to your formulas, right? The derivative of ln x, and they're going to give you that whole speech. But now you can just go into that class and be like, I know what the answer is, and you're going to just say it. And it's like, how do you know that? You're going to be like, Jhevon told me. All right, so then let's actually do that. ln x, just to be finished. So this one is, there's a trick to this one, because you might realize that I don't really see any parts. There's like just one function, ln x. But see, that's the golden thing about integration by parts, because you see, you can actually put in a part that might not be visible, because any function is just the same as 1 times that function, and 1 happens to be a polynomial. Lucky, huh? It turns out that I can think about this as ln of x times 1. So what I can do here is I can think of this as an algebraic, this as a L, right? A logarithm. And so what you can do is let u be the ln, and let your dv be 1 dx. Your du is going to be 1 over x, and your v is going to be x. So your I is going to be equal to u times v minus the integral of v du. So that's going to be that. Now that's a basic rule. That's just x. And so you can get to the fact that the integral of ln x is x ln x minus x plus c. And that's a super nice formula. When you get to Calc 2, they're going to expect you to have this memorized. And yeah, now you actually know where it comes from. It's an integration by parts. The next one for the sine inverse function, it's actually pretty much the same trick. You just think of it as like 1 times something, right? So you see this guy, you would think of it as, well, that's just sine inverse of x times 1 dx, where that's going to be an a, this is going to be an I. So by Liotte, the u is sine inverse, which, by the way, even without Liotte, this should be obvious. Like, we don't know how to integrate it, so it has to be the part that we differentiate. Same thing with ln, right? I couldn't choose the ln as my dv, because if I could actually find v, it means I would know how to integrate ln, and I wouldn't need to even do this in the first place. So yeah, so here we know that the derivative of this is 1 over the radical of 1 minus x squared, and that would just be x. So this means that I would be equal to u times v minus the integral of v du. Now this guy is not something that is a basic rule either, but it's not an integration by parts problem either with that. This is something that we could do with substitution, and we've done actually similar things here. So here I would just do a substitution. So I would do something like u squared is equal to 1 minus x squared. So this means that 2u du is equal to minus 2x dx. And so u du is equal to minus x dx. And so my integral is going to be minus u du replaces the x dx, and that guy's just going to be u. So this would just cancel, and that's just going to be minus 1 du, which the integral is going to be u minus u plus c, but my u was actually the radical of 1 minus x squared. So I'd go back and I'd plug that in. So this is equal to x sine inverse of x plus, because the minus of the minus. And you would get that. Let's just do one more, and I'll leave the rest for you to actually try. If you're thinking of, if you like integration by parts, you kind of like the groove, the rhythm, then you can actually, I'll definitely put an integration by parts, maybe a couple problems on the bonus to the final. You can practice the others and see you can do them. This one also has a neat little trick, because you'd start out with a substitution, but it's not terribly obvious what that would be. You have like an e to the radical x, which is weird to think about. But again, with substitution, you'd realize, well, the thing that's making it complicated is the radical in the power. So what you can do is I'm going to use a t substitution. And you'll see why in a second. Let t equals radical x. This means that t squared equals x. This means that 2t dt equals dx. And so I can get the fact that I would be equal to, if I call this I, e to the rad x. So that would be the integral of e to the t times my dx is going to be 2t dt. So you'll notice that this becomes te to the t. And now you can see why I didn't do a u substitution. I did another variable because this ends up being something that I need integration by parts for, and I don't want to mix up the u's. So at this point, I can do by parts. It's a guy we've seen before, so I'll just run through it quickly. U equals t, dv is equal to e to the t dt, du is equal to dt, v is equal to e to the t. So this just becomes 2 times u times v minus the integral of v du. So that's just 2t e to the t minus 2e to the t plus c. But our t was radical x. So you have 2 rad x e to the rad x minus 2e to the rad x plus c. That's your answer. So this also kind of tells you a situation in which it's not always obvious when a substitution can put you on the right track, because when you find the derivative of the substitution, you don't see it. It's like if I take the t equals rad x, the derivative is 1 over 2 rad x, you won't see that. But if you just rewrite the rad x as t again, so you'd have your dx is just 2t dt. You could also do it that way. Maybe I'll mention that. Or you could do dt is equal to 1 over 2 rad x dx. And so your dx would be 2 rad x dt, but rad x, you know, is actually t, so you can get that back anyway. Okay, that's that. So I would just say try the others if you have time. If you've studied all you can study, try the others. If you're done studying. Bored / want extra points. You definitely want to try every problem in the test first, because for the final, what I'd probably do is I will only count the bonus if you actually attempt all the problems in the original test, because technically, like especially integration by parts, is technically not a Calc 1 topic. Okay. That being said, I think we will stop there. I'll probably put the solutions to this in the actual notes when I post them online. But right now I'm not going to do them because we're already a few minutes over time. So yeah, and that's all she wrote. That's the end of Calculus 1. Hopefully that was understandable. I know it was like lightning fast. It's just that's just the schedule we were on. But we got through it. Good luck on the final. Good luck at the end of the class. I don't think anyone's doing too poorly in the class, so that's thankful for that. Have a good rest of your year, and I will see you guys in the final in a couple days. Well, maybe not see you in the next one, but see you around. Ciao.